So here we have our stepper motor. It's a 5-volt stepper motor from Lego. I'll have the link in the description if anybody wants to order more in the future. It comes with a driver board, which is a hugely important part of this equation. The jack at the end of this fits in one way into the board. Don't try to force it the other way. There's a jumper connector on top of these two pins that needs to stay there. Don't take them off. Here we have our positive and negative inputs for our power. We're going to be driving this from the Arduino's positive 5-volt and ground, but that's only for these experiments under no load. We're going to use an external power supply if we want to move any load, otherwise we're going to burn out our Arduino. On the other end, we have 4 input pins. Look at the schematic that'll be in the link, and you'll figure out which jumpers go from these pins to the Arduino pins 8, 9, 10, and 11. It's a unipolar stepper motor, which has 5 wires. One of them's the power in, the other 4 are 4 different coils that control the rotation of the motor itself. It's called a stepper motor because these motors have steps, they go in increments. These are 64th increments of a turn, but it's also connected to a gearbox. So those 64th increments actually have to turn 2,000 plus times to get a full rotation of the shaft. We'll have all that in the code set up and how many turns it takes to turn this once, and that'll be determined for us through the code, so we don't have to remember all the math, multiplying 64ths by the angle that it turns. But suffice it to say, this lets you make really precision rotations forwards and backwards with just using the code. It goes pretty slow in comparison to the DC motors we've used up to this point, but it's very accurate. So here we have the stepper motor and driver board hooked up to the Arduino. The only difference from the schematic that is in the link is that we're running the power from the positive 5-volt on the Arduino to the positive input on the board, and ground back to the ground of the Arduino. If you're going to put any load on this, do not run it with this configuration. I'll show you guys later how to hook up an external power supply for this. But for experimenting with the code and understanding it, this is fine for now. I've only put a little bit of wire onto the stepper motor shaft just to see it move. The other difference from the schematic is that I've created a voltage divider on my breadboard using a 2K resistor and a light dependent resistor. So that voltage divider runs from the 3.3 volt power supply on the Arduino. The other end of the light dependent resistor is going into one of the grounds. They conjoin in a row with a jumper cable that goes back to analog 0. And with this configuration, that'll let us control a little bit of the stepper motor's motion without just using code. The other important thing is that on the driver board, there's a little jumper next to the 2 inputs. Keep that jumper across those 2 inputs. We're not going to be taking that off or using that in any way. If it's not there, this won't operate properly. So just follow the schematic. In this example, pin 11 is going to in 1, pin 10 is going to in 2, pin 9 is going to in 3, pin 8 is going to in 4. Check the schematic, and we'll see what the code does. So here's the first set of code for the stepper motor. We're doing a couple of new things here in the code that we haven't done before. What we're doing at the top here is including a library from the Arduino program. So this one little sentence right here, what this does is it includes a lot of special case operations, things that happen in orange throughout our code without us having to specify too much. If you ever want to include a library, you can go up to the sketch, include library, and find what you're looking for. In this case, I chose stepper, and that'll include it in there for you. The other new thing here is we are creating an object for the stepper motor, something that the computer understands as a named object that is a stepper motor. So this first part, the orange part that says stepper, is telling it it's a stepper motor, and I named it Dennis Stepper. This could be cat dog, this could be door frame, it doesn't matter. I made it my own little whatever thing you want to name it, just to show you that it doesn't matter. What it says here, these arguments in here separated by commas, are how many steps the motor needs to take for a full revolution, and we're declaring that up here. Our particular motor takes 2038 steps to make a full revolution, with including all of the gearing inside of that motor. And then we're telling it which pins are going to be our outputs. Those pins are, in order, in a very particular order. You notice they're not sequential. We're talking ins and outs, positives and negative signals that will be going to the motor. As it operates, you can check out the LEDs that indicate which are on, which are off, and kind of see that operation. But that order of the output pins is very important. The only thing we're setting up in the setup is a serial communication speed so that we can kind of look at it. And in the loop, we've got it telling us which direction it's going to turn. The speeds in revolutions per minute. Don't go above 15 with these. They're kind of cheaply made, and any faster might strip the gears, tends to strip the gears, I should say. The other thing we're telling it here is not only the speed, but how many steps to take. So the dot set speed is one of the special pieces of information that's included in the library, and dot steps. So we have the name of our stepper motor, which we've declared ourselves, dot what function to accomplish with that stepper motor. I'm just using the variable integer steps here that we've declared up top. We can change that at any time, but 2038 is how many we need for a full revolution. We're calling for a delay, so we're going to go one revolution at a certain speed, wait for a second, and then turn around and do that at a slightly faster speed. Now the way we're turning it around is by declaring our steps as just negative steps versus just steps. So that's how we change direction with this. But again, 15 RPMs is as fast as I would go with this little guy. We're just learning. It's kind of a more educational tool than functional motor. So let's check out how this works. So I've uploaded that last little piece of code and powered on the Arduino. And thus far, this little guy's just moving in circles, stopping, turning back around. Now, the one thing you'll probably notice over time is that it's not the most accurate of stepper motors. Now, they make much more expensive stepper motors that have a higher degree of accuracy, but for the most part, you can kind of count on it going back and forth to the specified degree every time. The one thing that this is not, even though we can control its orientation very precisely with the code, what it does not know without some sort of code magic or external sensor is where in its rotation it is. So we can't, let's say, it doesn't know what 0 is for it. It knows where it is when it starts up, and it knows where it is when it finishes. And if we need to determine anything more, we'll need an external sensor of some sort, a switch, a button, or we can get fancier with the code, which we'll probably do later on, not right now. So here we have our second set of code. It's very similar in the setup and in the declarations at the top to our first set. We've got our library included. We've determined how many steps are full rotation for the motor, and we've declared what pins that motor signal is going to. All we're doing in the setup is telling it to talk back to the computer, and in the loop, we're just playing around a little bit with some of the speed, some of the turn rotations. In this case, before each turn, it's going to print out what it's about to do. So we're telling it to do a half turn counterclockwise, which we're making happen with this simple piece of math. Instead of just using the declaration of steps, positive steps in this case, we're taking that number and dividing it by 2. So it'll do a half turn, and then wait 700 milliseconds. For the next one, we'll be doing a half turn clockwise. Same thing with a negative. We're also setting the speed at each one of these. We don't have to set it every time, but in this case, I kind of wanted a small type of bouncing motion, so I'm making it go faster and take smaller steps each time. And to make those smaller steps happen, rather than changing a number, I'm going to be taking our total steps and just dividing it by quarters, by sixths, by eighths, by sixteenths, and letting the computer do the hard math. I don't want to do the math every time. And I'm also shortening the delay each time to try to give it that a little bit more of a emotive bounce each time it rotates back and forth, even though nothing's bouncing per se. So I'm going to plug in my Arduino and I'm going to let it run just a little bit without showing you the board yet, because I want to talk about the serial printing that's going to happen. So we're going to plug it in, upload it to the board, and once it's done uploading, we'll check out the monitor and see what it's telling us. So we can watch it in real time tell us what's happening, which this is where the serial print function is super helpful. We know exactly what's happening without having to look at the thing. And we can kind of see how fast it's happening too, because it does have that delay in between each one, which will delay its printing every time. So that's a fun way to get some information back out of it, and now let's look at what it looks like on the motor. So here's the code uploaded to the board and motor. Just watch it a sec. So the motor itself knows where it starts and knows where half a turn is from there, and then a quarter turn, then a sixth of a turn, an eighth of a turn, and then a 16th of a turn, and then starts again. But it doesn't, again, remember where it is, where 0 is when it starts. If I were to push the reset button on the board at any point in, it's going to think that's where its 0 is now. So be aware of, if this is important to the experiments that you're doing, that where it starts and where it stops, it doesn't know. It just knows what you tell it from where it begins. So if I wanted to control where it started, I could hit the reset button at the right point in its rotation, and it would start there again, like maybe there. Start at the top, work to the bottom. Anyway, so right now, what we're doing, because we set up the code in the way that we have, every time it stops and changes direction, it moves a quarter or an eighth or a 16th in that direction and then back the same amount. So we're ending at the same point every time, at that 180 from the start point. If we wanted to manipulate that, we can start doing fancier things in the code with math. Just start dividing that 2038 number in a couple of different ways and seeing how that plays with it. You can put in the number directly, or you can use the variable steps or whatever variable you decided to make it, but start playing around with what that number is to see how that affects its rotation, and even playing with how you do fancy math with the variable in that declaration to make this do slightly different things. So here's our last piece of code. It's pretty short, but it does some complex things. We've included our library again. We've declared how many steps in one rotation, and now we're declaring an analog in pin to read some feedback from the voltage divider that we created, and we're also making a variable just called turn. Right now it's set to 0 from the start. We're declaring our stepper motor, naming it, telling it how many steps, and the output pins. In the setup, we've only got one more added piece, which is declaring the A pin, the analog in pin, as an input. So we're just telling the computer, hey, read that, that's in, not out. And in the loop, it's pretty simple. We're going to read the pin, and then we're going to map that number. So we're going to take that variable in the map command. It takes the 5 arguments, what variable, the expected input, 100 to 800, which is what I observed when I did the analog read, that from the 3.3 volt and with the 2 resistors that I have, I got numbers between 100 and 800. So those are the first 2 numbers, which you expect to come in, and then what I'm turning them into. So if I left them on their own and used this to turn my stepper motor, I would only get between 100 and 800 steps, but my stepper motor can move much further than that. So I'm taking that smaller number and mapping it to a much wider range of numbers. So I can get numbers ranging from 50 to 2038 in the number of steps that my motor will take. I'm having it print that number to the serial monitor so that I can check it out, and then I'm setting the speed and where to turn. how many steps to turn with a small delay, and then I'm just doing the same thing in the opposite at the second part of the code. So we're doing the same read, same mapping, printing that number, but now we're just telling it to do a negative turn, anti-clockwise or clockwise, as it were, rotation. And if we check out the serial monitor, we can see the numbers roll in. And if I cover the sensor, those numbers should go higher. And if I put a flashlight onto the sensor, it should go much lower, giving me smaller turns. So let's see what this looks like now that it's uploaded to the board, and we can get some interesting motion out of it. So now we have the third piece of code loaded up onto the board, and we're reading from this voltage divider here. And so as I cover that sensor, it should give me a number that creates a longer rotation for the stepper motor. And as I give it more light, it'll create a slightly smaller rotation. And if I hit it with a lot of light, that'll give me much smaller rotations, much smaller sets of turns that I can now control with a little bit of in and out from the voltage divider. We could set up parameters with if statements. Depending on what those numbers are, we can make different sets of motions. We can have conditions set upon it as far as what that input to output is. All of that is yours to play with. And again, don't put any load onto these motors now that we're just powering it from the Arduino. I'm going to have links in the description to a good power supply for this, and show you in just a second how to power this externally with a 5-volt power supply. So now we have that same third piece of code loaded up onto the Arduino, but we're powering the servo motor externally, and it's a very different way to power it. The reason we're doing this is that if we put strain on the motor, it's going to increase its amperage draw across its coils, and that can exceed 200 milliamps, which is the maximum rating of what these Arduinos can handle. So in this configuration, if we put strain on it, it's going to be drawing power from our external power supply instead of from the Arduino, which will keep the Arduino from over amping and burning itself out. So let's explain what's going on here a little bit. Our positive and negative from the driver board are now coming over to our breadboard. This side of the breadboard, and this side only, is plugged into our 5-volt power supply. In the description, I'll have a link to the supply and to these handy little barrel jacks, which lets you plug it right in. Handy dandy, nice and safe. Positive and negative are hooked up to the positive and negative rails. Our voltage divider I've brought out a little bit further. I've brought one of the grounds and the 3.3 volt power out to this side of the breadboard. So the 3-volt power and ground are out here. The 5-volt power and ground from the external supply are over here. It's very important that we keep those separate. Our voltage divider is set up the same way, with the LDR in the negative, the 2K resistor in the positive, and we have this yellow jumper going back over to analog 0. The one thing you really don't want to forget is we're adding another jumper from one of the grounds on the Arduino over to the ground on the power supply. We're linking our grounds here so that all the electricity essentially flows to the same place and dumps into the same ground. Ground is ground, it doesn't matter where it's coming from. So we're powering our Arduino from the computer, not from the 5-volt supply. We're powering the stepper motor from the 5-volt supply. However, both of them, all of their grounds, are going back to a common ground in the earth. So we just want to make sure we have this jumper connecting the two. You'll see a tiny little thing like that on the schematic. But we just want to make sure our grounds are common between the Arduino and the stepper motor. Outside of what I've just described, everything else is the same. All of our pins, 8, 9, 10, 11, are connected to the same ins on the driver board. And our voltage divider is the same configuration, and we're just reading from there. So if we check this out, we can see with some more light, it'll start making shorter strokes, shorter turns. And with the dark, it'll be much longer. And again, in the code, you can determine what this distance is, what the stroke is, by changing the number of turns that you map the turn variable to. So have fun, play with these numbers. If you do order these power supplies, please follow this video very specifically so you don't put the wrong power in the wrong places. Again, I can't reiterate enough that now and only now I do not have these two sides connected with the same hots. They are essentially linked by the same ground, because ground is ground, but be careful. Have fun.